Hello, good morning, everyone, and welcome to the Group on Earth Observation Virtual Symposium for 2021. We are here in this session called Mountains at GEO, convened by the Group on Earth Observations Global Network on Observations and Information in Mountain Environments, or GEO Mountains, which is also co-led by the Mountain Research Initiative and colleagues. So before we start and introduce the session itself, just a few housekeeping guidelines. Please change your name to your organization and full name so that we can easily identify each other, also for networking purposes when we are joining the Wonder Me session afterwards in the coffee. Please mute your audio when not speaking. That would be appreciated. There will be a Q&A session at the end of the talks. Please click raise hand to request the floor, and the moderator will then invite you to verse your question. And the question should be addressed to one or more of the panelists. Feel free to make your comments or questions known. Also, any comments are welcome in the chat, so feel free to use the chat function to also communicate and share your thoughts. Please be aware that the meeting is being recorded, so please be mindful of that. And the Twitter feed for the GEO Symposium in general, use the hashtags EO4Inclusion or EO4Impact. Next slide, please. So what we aim to do in this session, Mountains at GEO, this is to give a flavor of some of the range of activities by GEO Mountains and many partners and participating organizations at GEO that also focus their work on mountain-related topics. So this is an opportunity to bring them all together for us to get a sense of what's happening across the work program, GEO work program. And this will hopefully also stimulate potential collaborations, not least among other GEO flagships, initiatives and community activities for the next work program period. Next slide, please. So just a brief introduction as to where GEO Mountains is at. As I mentioned, this is a global network initiated and co-led by the Mountain Research Initiative and the National Research Council of Italy. And within the context of this current implementation plan period 2020 to 2022, we are focusing on these four main objectives, which is about being able to identify data and information needs for a diverse range of stakeholders that operate within mountain environments, to be able to improve monitoring and understanding of mountain processes and phenomena, and to build, connect, and communicate with the community of mountain researchers, practitioners, and policymakers. That dialogue is absolutely important to be able to foster. And to develop that collective reporting capacity that responds to pre-identified assessment and policy needs. And we are finding that this is particularly important to have the coordinating capacity to do so. So this is one of the main reasons for MRI also investing its efforts into GEO Mountains. Next slide, please. So just to give you a recap of some of the recent news and accomplishments that we've managed to achieve in the past year, we have now put together a dedicated website that would allow us to give more information about the activities, the planned activities, and also the many associated and related projects that are out there. That are aiming at, in fact, supporting data and information accessibility in mountain regions, and also to increase the monitoring capacity that we need to improve. So feel free to please have a look at the GEO Mountains website, and your feedback on it is also absolutely very welcomed. Next slide. Another second recent news that we would like to share with you is much of the collective effort among contributors to GEO Mountains have also generated some very important research pieces and opinion pieces published in peer-reviewed papers, which allows us to also speak about the sorts of needs that are necessary to achieve improved monitoring in mountain spaces. For example, essential mountain climate variables is one of the three papers in a series of papers that we wish to put out there around the concept of essential variables more generally. So this first paper talks about climate-specific variables in more detail. And again, these are proposals that the community has put forth, and we would like also to receive comments to build on this concept going forward. Likewise, the idea of mountain observatories, the status and prospects for enhancing and connecting a global community is a recent paper that also highlights some of this collective effort. MRI has been around now for 20 years, and building a community to be able to discern some of these improvements and prospects for improving into the future are highlighted in these papers. Next slide, please. And the third brief news that we would like to share with you is one of the key tasks within the current implementation plan is to improve the way in which we put together inventories to be able to document more accurately and more systematically the sorts of in situ observational infrastructure that exists out there that is monitoring conditions in the mountain space more specifically. Now, this in situ observational infrastructure has been in development for many, many years, and we've taken now the opportunity to improve on this and systematize it, and this will be something that will be presented, in fact, on Wednesday as part of this particular GEO Symposium in a parallel session at 6:30 Central European Summertime tomorrow, Wednesday. So feel free to join us there to see the full presentation on that. Next slide, please. So we have here a range of stakeholders and partners with whom we collaborate around mountains, as I mentioned earlier. So we would like to now introduce each one sequentially to be able to give them the floor for them to outline some of the key work that they've been undertaking on mountains under the scope of GEO Mountains as well. So first up is Dr. Roger Sayre from the USGS, the US Geological Survey, who will be presenting on exploring mountain delineations and mapping and better protecting mountain ecosystems. And with that, I hand over to, just before I do so, perhaps if we go back one slide, and just to give an overview also of the other speakers that are coming up. So we also have Ruth, Dr. Ruth Sonnenschein from ORAC Research, who will be talking about one of the projects that have been funded through the GEO work program. This is using artificial intelligence to validate and downscale ecosystem-related essential biodiversity variables in mountains. So we'll hear from Ruth eventually. We also have Dr. James Thornton from the MRI Coordination Office, and who's also looking after GEO Mountains, and who will be presenting alongside Dr. Daniela Ehrlich from the European Commission, the Joint Research Centre, who are jointly putting together also characterization of the distribution of human populations in mountains, a reproducible comparative analysis, which is something that we are also contributing within the context of the Intergovernmental Panel on Climate Change 6th Assessment Report. And finally, we also look forward to hearing from Dr. Mandira Tresha from ICIMOD. This is the International Center for Integrated Mountain Development. And she will be presenting on Earth observations for disaster risk reduction in the Hindu Kush Himalayan region. And finally, we'll wrap up this session with a question and answer opportunity to engage with the speakers. So first up, Roger Sayre. Roger, the floor is yours. Thank you.
Thank you, Carolina. Good morning. Roger Sayre here from the US Geological Survey. I'm very happy to be here. Thank you for your interest in this presentation on global mountains. And thanks to the organizers for the invitation to present. And let me start in the spirit of full disclosure. I know everybody has their favorite mountains, and these are mine. I'm from California, and this is a shot of the Eastern Sierra Nevada mountain range with the minarets there on the left and Mounts Ritter and Banner on the right. Spectacular mountains and spectacular mountain ecosystems indeed. And shortly here, we'll get into the sort of the difference between mountain extent and mountain ecosystems. Okay. Next slide, please. Thank you. Here's the outline. I'm going to have to race through sort of a three-part presentation, beginning with a discussion on global mountain extents and framing that on the use of a tool that we built as a contribution to GEO Mountains called the Global Mountain Explorer, and then shift into a discussion on global mountain ecosystems and framing that brief discussion on a new product called the World Terrestrial Ecosystems, and then wrapping up with a brief discussion on a new tool that was developed by the IUCN for prioritizing mountain KBAs, key biodiversity areas. Okay, next. I hope some of you may be familiar with the Global Mountain Explorer. It is a web-based explorer tool for visualizing and querying global mountain extents according to the three most well-known concepts that are out there for mountain definitions and methods for mapping mountain extents. I have called those three concepts K1, K2, and K3. And the Global Mountain Explorer 2 really allows you to compare and contrast those. You can select K1, K2, or K3 in the map viewer and typically just pan around, zoom in and out, and query the data in a very map-centric way. Next slide, please. The K refers to the last name of the author of the publication about that resource. So K1 refers to the year 2000 publication by Valerie Kapos. That's K for Kapos. K2 refers to the 2014 publication by Christian Korner et al. That's K for Korner. And K3 refers to the 2018 publication by Denise Karagule, K for Karagule. Institutionally, K1 is associated with UNEP's World Conservation Monitoring Center, WCMC. K2 is associated with the Global Mountain Biodiversity Assessment, the GMBA, and K3 is associated with USGS and ESRI. And here you can see K1, K2, and K3, their global mountain extents. And at this sort of way zoomed out level, they look pretty similar. And in many ways, they are very similar. And then in some ways, they differ quite substantially. And that's because each one uses a different definition for what is a mountain and a different approach for how to delineate mountain extents. And again, the Global Mountain Explorer tool allows you to compare these three different concepts. So I encourage you to actually pull up that tool and range around, look at your favorite mountains. It can be very interesting to see how different areas of the planet were mapped as mountains or not mapped as mountains according to these three different approaches. And importantly, we are just now completing a new version of the Global Mountain Explorer version 2, which now uses the original K1 and K2 data layers. We had been using downsampled versions of K1 and K2, but we found that they tend to over-report the area classified as mountains. And so we have discussed that with the authors and their institutions. And we decided to go back and put in the original K1 and K2 layers into the new version of the Global Mountain Explorer. So we have swapped out the downsampled versions and swapped in the original K1 and K2. K3 is unchanged. So again, I encourage you to check out that tool. Next slide, please. And now moving into a discussion on mountain ecosystems. Shown here is a map of a new product called the World Terrestrial Ecosystems that was produced by USGS, Esri, and the Nature Conservancy. Next slide, please. And here you see the paper which describes that tool. Well, we identified 431 world terrestrial ecosystems, and it turns out that 77 of those are natural or semi-natural mountain ecosystems. And in that paper, we also did a gap analysis of the protection of ecosystems in IUCN protected areas. And again, the 77 mountain ecosystems, well, they're mountain ecosystems because number one, they occur on mountain landforms. And then number two, they are different in their climate regimes, both the temperature and the precipitation regimes. And then finally, they also differ in the vegetation assemblages or land cover found on those mountain landforms. Okay, next slide, please. And here I've listed out just a few mountain ecosystems. They're underlined in red. And you can see the global distributional area in the second column, as well as the protection or their representation really in IUCN category 1 to 4 protected areas in that third column. And then finally, their protection or their representation in all protected areas in that fourth column. So that's just a few examples that I took out of the GIS database. But the point is, for every mountain ecosystem on the planet, we know it's the area of its global extent, we know its exact distributional location, and we know its protection in protected areas. Okay, next slide, please. James, thank you. So what can you do with that kind of information? Well, IUCN has developed a new decision support tool for prioritizing conservation action among different mountain KBAs. A KBA is a key biodiversity area. That means it's an area that's important for species level biodiversity. And there are a lot of KBAs on the planet. And it may be that some of them need to be prioritized for conservation action more than others. And so IUCN has developed a tool for supporting that process. Next slide, please. And here's how it works. This is the Jammu Kashmir region in the Western Himalayas. And every polygon blob that you see there, those are KBAs, sites that have been identified as important for species level biodiversity. And now if you had to choose which is the next KBA site that you would want to prioritize for conservation action, well, using this tool, you would probably decide that that large KBA in the approximate center of this region, that red blob there, that's the one that probably is most deserving of conservation attention because it is a KBA, so it's important from the beginning for species. It's a mountain KBA, and we know that it is inadequately protected, and we know that because it has a yellow border, and if you look at the legend under KBAs, yellow means inadequately protected. And then we also know that it contains largely inadequately protected mountain ecosystems because it has a solid red fill. And again, you go to the legend, solid red means inadequate protection of mountain ecosystems. So that's how you would use that tool. I encourage you to get the tool, and there's a publication associated with that as well. Very interesting work. Okay, James, thank you. Here you can see listed out some of the locations on the web for some of these resources that I have discussed. And here again, you see those spectacular California mountains. Those are the best mountains in the world. There's no contest there. And finally, I would just like to acknowledge a lot of support from Esri over the years in helping me to map global ecosystems, including global mountain ecosystems. And I'd like to acknowledge my colleague from USGS, Jill Kress, who built the Global Mountain Explorer. And then I'd like to thank everyone in GEO Mountains, and in particular, Carolina and James. Thank you very much.
Thank you very much, Roger. As always, a very informative and fascinating way to see how many of the tools that have been developed by USGS have seen also application in practice, and in particular, the IOCN tool is very novel indeed. If there are no immediate questions for clarification, I would like to encourage everyone to hang on to any questions or comments you would like to raise with Roger for the end of the session, so that we can now move on to the next speaker, Dr. Ruth Sonnenschein at ORAC Research. Ruth, the floor is yours.
Thank you very much. Good morning, everyone. So I put here a picture of myself because my video is unfortunately not working. So my talk is about using AI to validate and downscale essential biodiversity variables, so-called EBVs in mountains. Next slide. The title is also the name of a project, which in short is called AI for EBV, that we were granted within the first joint call of GeoBon and Microsoft last year. Ecosystem extent and fragmentations are key EBVs in mountains to monitor and understand changes. Thus, ecosystem maps are not only needed to know where they are on the planet, but also how and where these are changing over time. While Roger just showed us a global map of them that he basically put out last year, it is not clear how these map can be used by stakeholders dealing with mountain areas. First, it has not been validated, and second, its spatial scale in terms of pixel size is rather coarse. So ABV is exactly stepping in here, and we deal with these two open issues. And we use EU data to generate ecosystem maps through time, thereby enabling a comprehensive assessment of ecosystem change and fragmentation. Just in a short. Next slide, please. So you have already seen this map, which Roger was just showing. And this map basically integrates 3 different data sources, which are the world climate zones, which mirror the macroclimate, world landforms, which modify the macroclimates into mesoclimates and microclimates, and land cover, which shows the major plant types, but also the human footprint. In its current version, this map has 431 classes, a spatial pixel size of 250 meters, and is not updated through time. Next slide, please. So our specific aims in AI for EBV are first to validate this WTE map, second to downscale the WTE land cover map part only from the 250 meter to 30 meter pixel size in order to combine it with the climate and landform layer backwards to come up with a better WTE version overall. And third, to downscale the WTE map itself. So we thereby focus and develop workflows for 2 mountain test sites, which you see in the background figure. In the following slides, I will only focus on the downscaling of the WTE land cover map itself, as we have been working on this topic in the last months. Next slide. So in order to downscale the WTE land cover map, we make use of an EU-based mapping workflow, which you can see in a very, very simple sketch on the left part of the slide. So key to the downscaling itself is this, let's say, generation of automatic training data, which are mainly based on the WTE land cover data, but not only. This comes with a lot of questions. So first of all, how good is this WTE land cover label for a certain class? And how can we use EU data to generate training data or help to exclude wrong training data? Which other land cover data sets can further be useful and for which classes? And how far do we get when we only use global data sets compared to regional ones or local data sets? And then last but not least, how is this affected by this class scheme and the quality of the data set? So in the next slide, I can here give you like a deeper look into the class-wise training data generation, which makes use of the previous validation actually that we did on the WTE land cover map. This classes strongly differ in the overall area, as you see here, as the numbers on the heading are given or are provided or are giving you these percentage for the European Alps, but they also differ in their spatial pattern. So you see here on the left side, for example, that for half of the classes of the WTE map and further EU data are sufficient to generate training data, such as for snow and ice, the water class, the settlements class, and the forests. So for these classes, we actually can use existing EU methods, such as spectral indices, to highlight pixels that can then be used as training data. For example, is the NDSI, the normalized difference snow index, or the NDBI, the normalized difference build-up index. The classes croplands and bare areas benefit from external land cover data, while training data for grasslands and shrublands are solely based on land cover data sets, which actually shows that these are not well mapped within the WTE land cover map. To come up with a rule set, we tested several global to local data sets with different class schemes and spatial scales, which you see on the bottom of the slide. Next slide, please. So our second topic where we step in with AI for EPV is also that we basically compare different AI-based classifiers, such as machine learning and deep learning classifiers. So the main difference is that machine learning uses handcrafted features, which can be pretty time-consuming and costly to set up. So deep learning learns the hierarchical structure from the data itself, but also scales with more data. And in our work currently, we are testing different random forest classifiers and deep neural networks to understand how performant and efficient these classifiers are. Next slide. So just to give you an overview how these actually work, because we entirely developed our workflow in the cloud that we were given. And this actually helped us to set up a scalable processing framework, which we couldn't have done on our local machines. In short, we developed a Python 3-based software stack to train machine learning and deep learning models, both on CPUs and GPUs. And the entire process can be regarded as a circle, which is managed by a data scientist and an EO scientist who are closely interacting to improve the downscaled land cover data in a constant way. Next slide. Coming to some outputs that we have generated so far. To start with, we have downscaled the land cover for 4 different tiles for the Central European Alps, of which each of them covers 100 kilometers in length. We used all summer images with a cloud cover of less than 70%, which sums up to 40 to 80 images per tile. The processing in the cloud took around half an hour per tile, and with overall costs of around $200. So in the middle, you see the WTE land cover map on the top, while the 2 figures below show 2 downscaled land cover versions, which include training data from different land cover maps that we have tested. So you see that the overall patterns are the same, but there are larger differences in some classes. And these are exactly the classes which strongly depend on external land cover data sources and also their underlying class scheme. And this can be especially seen in the class grasslands, which is mapped in certain land cover products as a land use class, and it's assigned to the croplands. But in other land cover data sets, this is just grassland land cover class. We have also performed an independent validation, which I don't like to leave unmentioned here. For this, we took the Lucas sampling points data sets, which is based on field widths across Europe across the last years. So this validation for now is heavily biased by the too low number of sampling points which we are using, and it does not mirror what we actually see when we look at the maps. So I just wanted to show here, we are in the process of doing this, but the results, they can't be interpreted in a good way as they are for now. Next slide, please. So by now, summing up, we have developed a workflow that allows us to test and downscale land cover using AI in the cloud, which would not have been possible without or on our local servers. And while we still need to invest some time to do some outstanding tests in order to come up with a workflow on which data to use in which context, we are also ahead of the next steps. So these will be the transfer of our workflow to the Kush Himalayan test site, but also through time to see how stable our workflow is. We will then generate a new WTE version based on the downscaled land cover data set and combine it with the landforms and the climate layer. In the midterm, we will assess this direct downscaling of the WTE label itself. And some upcoming information is that we will also put our outcomes on the GeoBon homepage, that it can be accessed by others and evaluated. And with this next slide, with this slide, I would actually finish my talk and thank you all for listening.
Thank you very much, Ruth, and fascinating results so far with the project that we put together also under the scope of GEO and GeoBon. It goes to show just how important those types of funding opportunities are to ensure that our community collectively comes together to generate such information, which is not only relevant for scientific purposes and to improve our methodologies, but it also has quite a bit of relevance in the context of conservation and protected area understanding. So thank you very much for that presentation so far. Next up, I'd like to invite my colleague James and Danielle Ehrlich as well from the European Commission to present on characterizing the distribution of human populations in mountains. Over to you. Thank you.
Thank you very much, Carolina. Yes, indeed, this is a joint presentation with Danielle Ehrlich from the GEO Human Planet Initiative, and also several other colleagues, including Carolina and Roger, who you've already heard from, in addition to colleagues from ICIMOD, GMBA, the Global Mountain Biodiversity Assessment, and the University of Zurich. So why is it important to understand a little bit about the distribution of human populations in mountains? Well, there are several reasons. But for instance, to understand what changing mountain ecosystem services could mean for society in mountainous regions, to more equitably or proportionally resource or fund environmental management, risk mitigation, and climate change adaptation measures, and to ensure that valuable mountain ecosystems are adequately protected from population pressures. So how can we go about this? Well, if we just have a small number of rather simple polygons, then we can use this excellent tool called PopGrid Viewer, which has been set up by CISIN, Center for International Earth Science Information Network at Columbia University. And this enables one to either draw or import polygons into a web application and to obtain comparative estimates of the number of people living within these polygons according to various different population data sets, which are shown here on the left. And one can also obtain some very useful and interesting and important information, technical information about the approaches underpinning these various population grids, which are vital really to consider when interpreting the results. So this is what we see in the table here. And so if we do this for the Alps, we see this polygon here delineating the Alps. For various different population data sets, we see a rather consistent result of just over 10 million people according to each population grid. But it's very important to note that if one were to consider a smaller geometry, one would probably see larger differences, not least due to the different spatial resolution of the various population grids. So this is really an important thing to remember. So this is great for an initial view and very intuitive for policy makers to go in and have a quick look. But if we want to introduce more geometries and more complex geometries, and perhaps also introduce additional data into our analysis, then we need perhaps a more bespoke solution. So in this context, our work here is seeking to really build upon previous studies which have already been conducted into the question of how many people live in mountains, to develop a solution and an analysis which is firstly more comparative, so looking across a wider range of population grids, and also the mountain delineations which Roger presented earlier, which is importantly fully reproducible and uses exclusively open source data and software. We hope to deliver data sets at aggregation or reporting levels which can be directly used for important assessment exercises such as those by the IPCC and IPBES. There's less sort of translation work required, so to say. And related to that, we want to provide the data in easily usable formats. So certainly exporting shapefiles with the population data attributed, population counts and densities, and also the areas of these shapefiles, and also potentially serve these data as through a web mapping application to enable people to zoom in and out and to query the data. Additionally, we hope to conduct an analysis which is a bit more explanatory than previous efforts, seeking to explore what actually controls or influences the distribution of populations in mountains. Is it climate, topography, or other variables? And this could provide some insights into how mountain populations might evolve in the future, given under changing demographic scenarios and also changing climates. So our input data are the three, in addition to the population grids, which we just saw, and we have these from 4 different sources, are the 3 mountain delineations which Roger presented. And I make the same comment here that Roger did, that whilst these mountain delineations look fairly similar on a global map, they actually cover quite a contrasting proportion of the global land surface, excluding Antarctica, which are shown in these percentages here at the bottom of each map. We have 5 separate data sets of polygons for aggregation and reporting. So we have here on the top right the IPCC regions used by the working group 2 in the current 6th assessment report. We have some sub-regions which are used by the IPBES. We also have the mountain inventory, the new version 2.0 from our colleagues at the GMBA here, which provide named polygons for various different mountain ranges in the world in a hierarchical system. So this data set will be released soon, I understand, but we can use it already for this analysis. And then in addition, we have the world climate regions, which have contributed to the world ecosystem map, which both Ruth and Roger have already talked about. And then we also have some hydrological catchments as well, which are another final reporting set. In addition, we have 2 alternative ways of mapping the extent of urban areas. So our workflow is entirely scripted, using predominantly PostGIS and GDAL, which makes it not only completely reproducible, but also easily modifiable and extendable. And to this end, we will wrap everything up at the end of this project in a knowledge package for the Geo Knowledge Hub, which we're looking forward to very much. So all these combinations of input data provide actually a wide range of results, which we can present in various different ways. But if we look firstly at a sort of global overview, here we're seeing the global population increasing fairly linearly through time from 1975. And in the year 2015, where we have estimates from all of our 4 different population data sets, we see an extremely similar figure. Then below we have our estimates of the so-called mountainous population, the population which falls within our mountainous areas according to the 3 different delineations. Again, we see a fairly linear increase, but at a rate which is slower than the global rate. But the really remarkable thing is this range here at 2015. And this shows that actually, depending on the combination of input data sets we use, the mountainous population could range from as little as 344 million all the way up to 2.29 billion. And the major factor here is the mountain delineation, because we see these sort of groups here. All these points correspond to K3, which is the most generous delineation, then K1, and then K2. So really, this is really makes a big difference. But then in addition, we have some variability within the group, and this corresponds to the choice of population data set for a given mountain delineation. So this is also somewhat influential, although the effect is definitely secondary. We can look in a spatial regard, for instance, looking at the mean population density across entire regions compared with only the mountainous proportions or mountainous parts of those regions. So doing that here for the IPCC regions, looking at K2 and Landscan as our source of population data in this case, we see that in Europe, the population density in mountainous parts is actually substantially lower than the overall population density. But interestingly, this situation is actually reversed in Africa, where the population density in the more limited mountainous areas is actually considerably higher than the overall mean density. And so there could be some implications for this potentially under changing climate. Will this situation be analogous to species, vegetation species, which might have nowhere to go, or will populations there be able to adapt to change? We can look similarly at results in the spatio-temporal sense, here looking at simply the population count through time against the GMBA polygons. And we see, for instance, which regions are increasing in population fastest or most. And we see, for instance, that certainly the Himalayan region here seems to be increasing in population considerably, which may have some implications for natural hazards and disaster risk reduction, which Mandira will talk about afterwards. As I mentioned, an additional polygon set, which we wanted to report our results against, are the world climate regions, which, as I said, contribute to the ecosystem map of Roger, shown here on the right. There are 18 of these. And we're looking now at the mean population density, again, for the entire regions in green here, but then only the mountainous proportion in the sort of blue or gray. For K1 and the global human settlements layer population data set, which comes from our colleagues at the GEO Human Planet Initiative. And so here we see that for most regions, the population density in mountains is lower than the overall population density, but actually in 3 cases, this is not true and the situation is reversed. So there seems to be a sort of pattern here in that in somewhat dry climates, the population density is actually higher in the mountainous portions, which suggests that the mountains may provide a sort of refugia for populations in dry climates. In contrast, in some more moist climatic zones, there's actually a strong difference, and the mountainous population density is considerably lower than the density overall. And this could suggest that in such climates, people don't either need to live in mountains or that the conditions are more inhospitable. So this is kind of interesting. We would like to explore this a little bit more. Finally, moving on to urbanization, we see that whilst the global urban area is extremely small, less than 0.5%, it corresponds to almost 50% of the total global population. And if we now look at the proportion of this urban population which falls within mountains, we again see a large difference according to the data sets we use, so between 2% and around 23%. And this sort of makes sense that in the sense that we know that there are many large cities in sort of this transition zone between mountains and non-mountains. Looking here in yellow, we see the urban extent according to the Global Human Settlements model here, and we see that not very much falls within K2 at all, but some does fall within K3, and this is really responsible for this difference in the results. So to wrap up, we hope to introduce further climatic and topographic data to explore these associations a little bit more within individual mountain regions, and then we have a paper to write. So that's all from me. Thank you very much.
Thank you very much, James and Daniela, for this really fascinating analysis and the importance of understanding the approaches and methodologies that are applied is really important to understand how those figures are in fact generated. So we look forward to the paper indeed. And finally, I would like to invite Mandira Thresha from ICIMOD to take us through examples of Earth observations for DRR in the Hindu Kush Himalayan region. And in the meantime, if you have questions, again, please feel free to hang on to your questions for the Q&A after Mandira's presentation. Thank you very much. Mandira, the floor is yours. Thank you.
Thank you, Carolina. A very good morning, good afternoon, or good evening, whichever time zones you all are in. Can I have my slides, please, James? I do not see it yet.
You have control, actually, Mandira.
Okay, here we go. All right, thank you very much. Yeah. Okay, well, I'm going to be talking about Earth observations for disaster risk reduction in the Kush Himalayan region. And to start with, I'd like to just give you a background of the key issues of the region. So if I just go to the next slide here. Yes. So the key issues in our region is that we live in a multi-hazard environment, and whatever is happening in the upstream is very much affecting those that are living in the downstream. And that we all know that climate change and variability is having a great impact in the region, particularly the snow and ice. And then the region is extremely remote, many of the mountain regions, as you know. And so the connectivity is an issue, the access is an issue. And the governance issues are also quite challenging. So some of you who are not aware, the Kush Himalayan region is a range that extends about 3,500 kilometers from west to east, covering 8 countries all the way from Afghanistan on to Myanmar. So now, okay, so we go to the next slide, please, James. So we have done an assessment called the HIMAP assessment, which was launched several years ago in 2019. And this is the HIMAP assessment. And we had a chapter there on disasters. And there were several findings. The first finding is that, as we all know, the Kush Himalayan region is prone to various types of disasters. It's a hotspot for disasters. And that more than 1 billion people are at risk of exposure to increasing frequency and intensity of natural hazards. And then when you look at this, you can see that looking at the typologies of different types of disasters, floods alone account for more than 40% of all the disasters. And when you're looking at it in terms of the economic losses, it's about 52%. So it's quite a huge impact when we're talking about floods alone, as well as other different types of disasters. So when we are looking at these disasters, we see that the trend is increasing. So that's quite a concern for the region because it's really threatening the sustainable development in the region. Now, there are many different causes, as you all are aware. The first, of course, is the climate change and variability that I just talked about. But apart from that, there are many other anthropogenic causes, like James just mentioned, you know, the haphazard population increase in the region, the rapid population increase in the region is also contributing to greater disasters in the region. There's also urbanization that is taking place rapidly, but most of it haphazardly. You know, sometimes many of the settlements are coming in the floodplains, which is quite hazardous. And then the policies and plans that are in place are also not only inadequate, but also poor implementation. And then the investments also are very low in the region. And then the capacities in the region is limited and varies from country to country. And the governance and the arrangements are also quite challenging. Now, when we look at the report, the second finding is that there is cascading events. So it's not only one event that you're looking at, not only floods, but it could be also landslides or earthquakes or many different types of hazards coming together. So it is because we live in a multi-hazard environment, and what happens upstream, like I said, it also affects that of the downstream. Now, just recently, I say recent, this is the a big disaster that occurred. Some of you may have heard about it. This is the Chamoli disaster in Uttarakhand in India. And as you can see, this is really in very remote areas that these disasters are happening. And much of where the disaster is originating from is really at very high elevations, above 3,000, 4,000 meters, which is very difficult to access. So therefore, satellite imageries and satellite-based information becomes crucial in terms of better understanding of the processes as well as the risks that are there. And here in this figure here, you can also see that, you know, a lot of hydropower projects along the river were damaged because of this large flood that occurred just in March of this year, and more than 150 people were killed. Now, another example I want to really provide you is regarding this, well, it was just last week actually, a disaster, the flood disaster in Melamchi Bazar in Nepal, close to Kathmandu, where this large settlement basically got inundated. I mean, basically you can see these are these settlements that are being built in the floodplain. So unfortunately, this huge disaster occurred. Now, this disaster occurred mainly because of, you know, high intense rainfall, but also there has been a lot of landslides in the upper catchments, which have resulted in a lot of blockage And then sudden breach of these dams have resulted in large flows, debris flows that came down and inundated the whole settlement. So this is just last week as it's happening. It's still very fresh, and we are still looking for imageries, satellite imageries, to really better understand what the processes have been and where really the origination was. So here, I think it's important that we have quick access of these satellite imageries, where this platform itself, the GEO platform, could also be a vehicle for this quick access, which I hope would be. So now I'll focus on the third finding, that is these disasters basically have differential impacts. It affects men and women differently, and there are many reasons, definitely, primarily because women have less access to information, they are less mobile, as well as their decision-making power is also limited. Of course, they have limited access to these trainings. And in this region, in the Kush Himalayan region, there's a lot of gender-based sociocultural norms that really affect women in terms of this access to information. And also that there's huge male out-migration, so women are left to really face these disasters by themselves. So these are the three different findings. So what are some of the lessons learned from these disasters? First and foremost is that the observing networks, I think that was also highlighted by Carolina earlier in her introduction, is quite weak in the higher altitudes. So there's a need to really look into how we have a better observing network in high altitudes, so that we have better information data that could be assimilated into the models and have better understanding and better products. And there's also this limited data information, which is not easily shared in many of the regions. This is true. So when such disasters occur, it's extremely important that there's quick access to satellite imageries, like I have highlighted earlier. So this is something that we need to really work on, how to access these images. And then the institutional mechanisms become crucial in terms of communication and dissemination of flood information, not only flood, but disaster information down to the people and the communities. And often when the information is flowing, you need to really keep in mind the social and cultural perspectives. Now, in both these examples that I shared with you, there were some infrastructures along the river, whether it is the water supply project in Nepal or those 2 hydropower projects in India. So there's a need to really look into these risks, better understanding of these risks, and build resilient infrastructures. And one point that I wanted to really highlight, which would be very important also to keep in mind, is this, that we not only look at what the weather will be, but what the weather will do. So that is what it would be when you're looking at impact-based forecasting. So more look at impacts, what is it that it needs to be done? And overall, since disasters have no borders, we need to promote regional cooperation. So I think these are some of the key lessons from these past disasters. Now, there are ample opportunities, and when you're looking at the opportunities, then the first is that there is an opportunity to harmonize climate data information, a standardization and risk assessment methodologies across the region. And also because of these increasing disasters, events that are occurring in the region, there is also a need to look into increasing demand of climate services and increasing need of these partners in terms of utilizing Earth observations and improving their capacity for better responses, for better adaptation. And ICIMOD, being a regional organization, intergovernmental organization, is placed well to then address these needs, host these mountain-specific climate data and information. So this here you see this illustration, this image you see is from Servier HKH. And here you can see that there are 4 different service areas: agriculture and food security, weather and climate services, water-related disasters, and then land use, land cover, and ecosystem services. And we are very much closely working with our partners in NASA, as well as other partners that are there. Okay, next, please. James, next, please. Yes. So ICIMOD is then hosting this Himalayan GEOSS, and some of you may be aware that this is a task group under AOGEO. And what it seeks to do is address the gaps in Earth observations, particularly applications in those various sectors that I just mentioned. And it also provides a regional platform for sharing Earth observations and geospatial information, particularly to promote research and development. It also builds the capacities of the countries in the HKH region. And currently, I think just next month in July, the Regional Center for Capacity Building with AOGEO is going to be launched. In fact, my colleague Birendra Bajracharya, he's the key person in the Himalayan GEOSS who's coordinating this, and will be launching this together in July. So we very much is working forward to, again, fostering regional cooperation to address these common issues in the region to basically contribute to global knowledge on the mountain systems. Now, just some examples that I would like to provide you with the work that we've been doing. Just very few examples, actually. One is the Forest Fire Information System, where we've been working together with the government of Nepal, the Ministry of Forest and Environment. And so this here you can see, this year has been quite difficult in terms of having a lot of forest fires. And so this was a forest fire detection system that is in place and is working. The next example that I want to give you is the mapping and monitoring of the glacial lakes. And this has been done since quite some time. Actually, we started it in 2000 and we've been doing this since. So there have been 3 or 4 times that we have, reviewed and mapped these glacial lakes in the region and the glaciers in the region. And this is for the entire Kush Himalayan region. And this is particularly important because due to climate change and variability, there is an increase in terms of having more glaciers and more threat in terms of glacial lake outburst floods. So this becomes critical in terms of continuous monitoring of these lakes. Another example is the end-to-end flood early warning system, here utilizing real-time technology for transmission of data, for first collection of data, using also satellite-based information so as to fill in some of the data gaps that are there and providing that information down to the people at need. So this is another example that we are working closely with. So I think with those examples, I just wanted to highlight some 3 key messages that we had from the HIMAP report. The first is, of course, we need to work collectively together in terms of addressing the needs, and then looking at it to adopt a more of a multi-hazard approach, a standardized approach that is required. Then the second message that we have is that all the stakeholders particularly need to take urgent actions to build resilience, actions for enhancing resilience, and that we can do by addressing 4 I's, I call it. I haven't listed it here. 4 I's is looking at information, looking at infrastructure, looking at insurance, and institutions. So we need to look at all those 4 I's. And fourthly, we need to be collectively working together, since we are working across countries to share data and information knowledge, as well as foster transboundary cooperation for disaster risk reduction, and particularly utilizing these advanced scientific tools and techniques and Earth observations in the region. So with that, I'd like to thank you for your listening.
Thank you very much, Mandira.
Over to you.
Excellent presentation. And indeed, you highlight something very particularly important for mountains, which is the transboundary nature and the importance of regional cooperation, not least in being able to share data and information to address the many societal challenges that you've also highlighted in your presentation. Now, we are fast running out of time for this session, and we have included in the chat the link for you to have the opportunity to continue this conversation if you wish at the WonderMe coffee space. Just wrapping up though, one of the key things about this session, in particular the GEO Virtual Symposium for this year, the theme is really about strengthening inclusive partnerships across the GEO work program. And I would like to invite each of the speakers to just give a 30-second impression or message rather to GEO Mountains, and how could GEO Mountains help foster such a partnership going forward. This is important for us to be able to connect the dots across the work program community. Maybe if I can invite Roger for 20-second advice, if you like, for how GEO Mountains could improve that.
Well, thank you. And I see GEO Mountains is actually one of the parties that does that better than most in GEO. GEO Mountains has, I think from the beginning, indicated an interest in reaching out. And I'm talking about within GEO. GEO is a large world. There's so many initiatives and flagships, they call them. And GEO Mountains has reached out and tried to sort of very inclusively build that community of practice for those in the GEO community that have any interest in mountains thematically. And you know, I know that GEO Mountains is reaching out to, in the Americas, the Tropical Andes Observatory. I mean, there are lots of areas of common interest and people working on sort of very similar concepts, but from slightly different perspectives. And just hooking up those groups of people is a really good thing, and it's something that GEO Mountains values, and I think is doing very actively. So I think just continue to reach out and just look for ways where it's not just about the research that we're all doing, but about how that research kind of transcends into the policy making and decision making environment. There was a question about that, and that's what we need to do better. We're all such good researchers. We do research, we put it out there for other researchers to consume, but until it transcends into supporting decision makers, it's just not quite enough.
Spot on, Roger, and thank you very much for that really encouraging endorsement of the activities that need to be continued. Absolutely agree there. I would like to invite Ruth, if you've got a few seconds to spare, to tell us what your impressions are as one of these contributors within a GEO activity such as GEO Mountains. If you're still there. You probably. We'll come back to Ruth if she's still online. Perhaps Daniela has something to share.
Yes, hello, Carolina. Thank you for giving me the floor briefly. I echo what Roger said. GEO Mountains is one of those projects that really goes across continents, and so it's interdisciplinary and global in extent. And that is, we, part of the Human Planetary Initiative, have few projects to work with that have that spread. So congratulations to GEO Mountains. If I would have a recommendation, it would be for developing one aspect of mountains, and it is accessibility to settlements and city settlements, which was brought up in one of the presentations today, and which is typically neglected. And accessibility to services and so on is key also to the SDGs and all international programs, including Sendai and so on. And thank you for this excellent presentation and session.
Thank you very much, Daniele, and fascinating also to hear your thoughts about what could be improved. And indeed, this is something that we need to incorporate into the design of our next implementation plan. This is very good to hear. Finally, Mandira, would you like to share a few seconds, an impression for how to improve our partnerships?
Yeah, thank you, Carolina. I think much has been said already, and the point that was raised earlier, I think I would like to very much support that. But apart from that, it's also necessary that we look into how we build on each other's expertise, more collaboration and communication that needs to go across these different networks. And I'm really glad that we have GEO Mountains very much focusing on mountains, because much of the challenges that we have in particularly the Kush Himalayan region is so challenging that GEO Mountains can really address some of these very acute challenges that are there. Now, the example I was trying to show you, to really emphasize, is the need to have, for instance, these satellite imageries through the GEO platform. I think that is very urgent. And so if there is quick access to these satellite imageries through the GEO platform, and if GEO Mountains could really also, try to voice that, I think that would be really good. And, we also have, of course, the Himalayan GEOSS as part of AOGEO. But if we can collectively make that, voice, then I think these imageries could be made available, and particularly mountain areas, because it's so remote and there's nothing that can go up into 4,000, 5,000 meters elevation in a short time, because it's urgent when you look at risks, and with risks needs to be, reduced, that we have access to these imageries, and also for future kind of planning, it's urgent. So that is one message. I think it would be very important. So, along with satellite imageries, like the second one was collaboration and cooperation, more better communication between these different actors and different units that we have. And then third, of course, to work more collectively. When I say build on each other's expertise, then it would be also to see how we translate our scientific knowledge, the research knowledge that we have, into policy and practice. And I think this would be our ultimate goal, to see that we link it to the societal benefits, because that's where the whole purpose would be complete. So I think that's where we need to focus on, and then collectively try to look into these. So I think synergy is the key. We have to build onto each other's expertise and then move on, so that we can really support the mountain communities to be more sustainable and really meet those sustainable development goals and challenges that are ahead. Thank you.
Wonderful. Thanks very much for that recommendation, Mandira, and absolutely we take those messages and recommendations fully on board. I also see that Ruth has shared on the chat similar responses and reactions, and in particular the opportunity given to connect the research community, which, like mountain regions, they also tend to be very fragmented and spread around the world. And it is important for us to have these platforms through which we can help connect and bring together these different groups of people. So great that we have the opportunity to do that for the mountain research community as well. And on that note, I also would like to acknowledge Sarah Venturini, who's from the GEO Secretariat, who's very kindly also put the prospect to help us also scale and connect with the policy relevant forums that also GEO as a whole is entrusted to connect with. So thank you very much for that, Sarah, indeed. And with that, we've gone over time, so apologies for stealing some of your coffee time. Please feel free to continue to enjoy the many sessions that are available through the GEO Symposium this week. And of course, we very much welcome your comments. Some of the questions we could not have the time to address, so please feel free to send us an email and check us out at GEO Mountains website, and we'll love to hear and connect with you soon. With that, I wish you all very much all the very best. And yes, let's continue building partnerships for meaningful GEO collaboration. Thank you. Goodbye.